Alrighty, good day to you. It is Unit 4 Lesson 5 time. We are looking at changes over rational intervals. This is, again, we know that time input, where we're looking at inputs, that's our x's, that's when our exponent is now a fraction that we saw. So we're having box times box to the box over box, our starting, our multiplier, how much time we're giving it. Now it's usually time, I can't always say time, but it's whatever that input is that we're looking for over however long a cycle usually is, which is why this is mostly time. It's because we're talking about time cycles of how long something takes. So if we consider the exponential function h of x equals 4 to the xth power, what we're looking at, there is no starting value, so we can think about that like 1 times 4 to the x. So we would start with 1 of something, or maybe that 1 represents hundreds or thousands or whatever. And it's multiplying, growing it 4 times, so 400%, or quadrupling every single time we get through one cycle. So by what factor does h increase when our exponent increases by 1? That's saying if we go from 4 to the first to 4 to the second, well, 4 to the first is just 4, and 4 to the second is 4 times 4. So the factor that it's increasing by is 4. It's quadrupling. And so if our x increases by 2, that would mean we're going like 4 to the first to 4 to the third. That exponent is increasing. So we're taking 4, and this time we're doing 4 times 4 times 4. So it is multiplying 2 more 4s here, and so that would be 4 squared, which would mean it's 16 times larger. And that same idea, we're going to just keep on using this, whatever that change in our input is what our exponent is going to be. So this time we're saying going from something like 4 to the first to 4 to the 1.5. Well, 4 to the first is just 4. 4 to the 1.5 is 8. That's interesting. So it looks like it's doubling. Okay. And so let's see what that might mean. If we're raising it to the 0.5 exponent, 4 to the 0.5, you may remember that also as the same as 4 to the 1/2, or the square root of 4. They're going to start showing us some of our values written like that. And that equals 2, so it's doubling, which is what we thought here between that relationship. So as we change our input, we can use that still as an exponent on our multiplier, on our growth factor, and still be able to tell how our values would be changing. Now we're going to start using this here in a machine depreciation. So I want to remind you that that word depreciation means it is depleting, it is losing value. And lots of things depreciate after you buy them, right? You buy a car, drive it off the lot, it starts losing value right away. After a long period of time, a car becomes a classic, and maybe its value starts going up, but most of the time it's just going down and down and down. Same thing if you buy a computer. As soon as a company buys that computer or any kind of machinery, it starts to depreciate exponentially. So this table shows its value as a function of years since purchase. If we had a spreadsheet, we could use this because it could actually help us fill in some values in between, but we're just going to use our regular old calculator to make it happen. So our value of our machine in dollars is a function of time t. So it's a function of time t. So the number of years since the machine has been purchased. We want to find an equation defining f and be prepared to explain our reasoning. All right, so we're looking for how to fill in a function f of t, the function, this value based on time. Let's keep on using our box times box to the box. I like still thinking of that. Box times box, and we're going to raise it up to a box about what's happening. Okay. So in that first box goes our starting value. This machine, when they first purchase it, costs $16,000. So we'll put 16,000 here. Now, if you wanted to take away some zeros, we could do just 16. The value of the machine, yep, we'll just keep that 16,000 there. And we need to find our multiplier. We're going to bring this for every t years that's happening. So if we're looking for t, the number of years, well, we can find our value from 1 year to the next year. We want to find out 16,000. We need some kind of multiplier that we don't know. And after 1 year, it has to equal 13,600. 13,600. And so if 16 times something equals our new value 1 year later, to find what that multiplier is, I would have to divide both sides by that 16,000 to figure out what that multiplier is. And that multiplier is 0.85. So it looks like it only keeps 85% of its value. So that's our multiplier. We're going to put that here. So I just took a 1 year cycle and made sure that that happened. 0.85 is our multiplier. And I can also double check it. If I go from this year to the second year, it should also be that same multiplier. So if I do 13,600 times 0.85, I get the 11,560. And again, if I multiply it by 0.85, I should get 9,826. So I can tell that that's absolutely perfect. Now I think on my next question, it's going to ask me to fill in the unknown values of the table. So now that we have an equation that we know is working, I'm just going to use that same equation to fill in our years since purchase. 16,000 times 0.85 raised up to the 0.5 for a half year. And this tells me the value of this machine at that time. $14,751.27. Now 1 year later, I'm going to actually not use my equation for the next one, but I see that this is 1 year later. So I found a half year already. Now I want to go 1 full year later than that. 1 full year multiplier is 0.85. So on my calculator, I'm going to be smart and strategic. I'm going to take that value that I already have here and multiply it by 0.85 because this is 1 full year later. 12,000. So let me put that there, times 0.85. There we go. So now you see what I'm taking the number and how I did that. 538 and 58 cents. Now if I want to double check that, I certainly can using my function that we wrote, plugging in 1.5 years from the original purchase, and I get the exact same thing. So it's kind of neat to see it that way. So this is our idea from lesson 5, that any 1 year chunk, it doesn't matter if I'm going from 0 to 1 or 1 to 2 or 2 to 3, will have that same multiplier for 1 whole year. And even if I go from 0.5 to 1.5, as long as it's a 1-year cycle, it'll still have the 1-year multiplier. So that's really what they're looking at here when they ask us to observe some values in the table. By what factor did the value of the machine change every 1 year? It changed to 0.85, that multiplier that we have. And that was true from 1 to 2 years, and from 0.5 to 1.5 years. All of them were the same. So every 1 year change has the same multiplier. And every half-year change, well, if we were going to look at the half-year, we would have to take that 0.85 and we'd have to bring it to the 0.5 power. Every half-year is going to have a different multiplier. 0.922-ish. Okay. And every single half year is going to have that same amount. So if I needed to keep on filling half year amounts, 0.5, and so I could then complete this table by multiplying by 0.922. So 16,000 times 0.922 gets me really close to this number, times 0.922 gets me really close to this number, times 0.922 gets me very close to this number, because each of these is changing in a half-year amount. Suppose we know that f of q, well, we know a value for f of q in a year, the value of the machine q years since purchased, so we could use f of q to find f of q plus 0.5, meaning a half year later. Once we know one of those, we could take f of whatever value we have, if we know that, and we could multiply that by 0.922 to find what it would be a half year later. So just taking that half year multiplier and using that. So this would be our known value, and then this is our half-year multiplier. (5.3) gets us where we can really start to see what we might be working with and how we can apply this. So toxicologists use this. If you are becoming a forensic investigator or anything like that, they do like to look at this kind of stuff to see how long medicine has been in the body. You might use it for the medical field too, if they're trying to tell how long it's been since someone OD'd if you're at the hospital, or if they're trying to see how much medicine is still left in your body before they give you more medicine. They would use a chart like this to be able to tell. So if you're thinking medical field, or anything in investigations or criminal justice, you might be using this kind of stuff. Graph shows the amount of medicine in a child's body 8 hours after taking the medicine. The amount of medicine decays exponentially, so you can see this exponential decay, this reducing amount. After a quarter hour, so right here, there are about 7 milligrams of medicine left. So this point right here is telling me now a scale for my vertical. 7 milligrams are left. After 3/4 of an hour, there are about 3.5 milligrams left. And so now it's asking us about how many milligrams of medicine are left after 1 and 3/4 hours. 2/4, 3/4. It's asking me here at C. 1 3/4. Explain how you know. All right, well, it looks like going from here to here. So this is a ½ hour of time. Going from 1/4 to 3/4 of an hour. So that's a ½ hour of time. Okay, if you need a clock to think about that, here's 1/4 of an hour to 3/4 of an hour of time. This is 1/2 hour of time. Ooh, that's hard to see. Sorry about that. So in that ½ hour of time, the medicine goes from 7 milligrams to 3.5 milligrams. It's cutting in half. So we are thinking about how, I know this isn't really our starting point, right? But if we kind of arbitrarily start it here, that 7 milligrams is cut in half for every ½ an hour cycle. I'm going to call that H for a ½ hour cycle. So at our next ½ hour cycle here, here's a nice way to kind of show this. We can kind of complete a table and be thinking about this, that when we have 1/4 of an hour, we're at 7 milligrams. At, I don't know ½ an hour, but I know 3/4 of an hour, I'm at 3.5. I don't know 1 hour. I don't really care about 1 hour. But at 1 hour and 1/4, it's going to have cut in half again. So that 3.5 is going to cut down to 1.75. Now that's just 3.5 cut in half. And I don't know 3/2. I don't really need to know it. What I need to know is the 1.75, the 1 3/4 hour. It's going to be this value cut in half again. So divided in half again, and we would have 0.875 milligrams left in this person's body. So we can use this for each of our ½ hour chunks. So 1 ½ hour chunk got us here, another ½ hour chunk would get us here, another ½ hour chunk. So that's 1 ½ hour, 2 ½ hour, 3 ½ hour chunks. So those 3 ½ hour chunks, see how we're using this equation now to get us there, would find the same answer. So we don't have to make a whole table and find everything in between. We would do 7 times 1/2 in 3 ½ hour chunks would get us there. So how can the decay rate from 1/4 to a ½ hour compare to the decay rate from ½ to 3/4? Well, ½ to 3/4, we just said, cuts in half. And if I want half of that ½ an hour, I want 1/4 to ½ an hour, I would need half of that. Okay, so 1/2, 1/2 hour. Oh, wait. I'm sorry. Hold on. I'm thinking of this the wrong way. 1/4 hour to a ½ to 3/4 of an hour cuts it in half. I don't need half that time. It's asking us, sorry about that, editing my thinking as we go. This is real life math and how it works. It's asking us, how does the decay rate from 1/4 to 1/2 hour, which is a 15-minute jump, compared to the decay rate from half an hour to 3/4 of an hour, also a 15-minute jump. And so our big idea here from lesson 5, I don't even know what those values are. But as long as the time is the same, the rate is going to be the same. So that's our big idea. Same time span is the same decay rate. And the same would be true for growth. As long as I have that same time input changing, I'm going to have the same multiplier on the output. Nice. And we could go back and fill in our table and figure all that kind of stuff out, but really it's just going to be a half of a half or a quarter each time cutting through there. So we'd be losing 75% every 15 minutes. Alrighty. I think you're ready to go tackle lesson 5 practice problems. Maybe check that summary to see how we can make those comparisons, but we're really seeing that every single one of these would have the same fractional interval. Same thing's going to be happening with our same whole number intervals.